Hey again, this is the video for Tuesday about current. We're starting on slide number 8 for this one. So electric current is, put simply, the flow of electrons through a circuit. Um, the letter to represent current is a capital I. Doesn't really make sense as many of our variable representations of measurements don't. The I stands for intensity. I think it's an old-fashioned term that just never got updated and never will. So, just put that in there for the term maps, perhaps. Electric current's variable is an I, and again, it is the rate of flow of charge through any one point in a circuit. The way we measure current is with the measurement called amperes, abbreviated amps, or just capital A for amps. So if we put this statement into an equation, rate of flow of charge, anytime the word rate is involved, we're talking about it against time. So if current is the rate of flow of charge, it's equal to charge over time. Q for charge, T for time. And then the units again are the amp equals a coulomb per second. So now if we take a look at that equation again, current is charge over time. I'm just spelling it out here. This is just so we have it on one page. But one more detail I added here is that the ampere itself is named after a French physicist named André Marie Ampere. Most of our units in electricity are named after scientists. All right, so let's just take a look at an example of this new equation for current. Let's say we have 4 coulombs of charge flowing past a point in a conducting wire every 5 seconds. Okay, well, we've got a charge, we've got a time. I'm going to color them in for you in a moment. If we're trying to solve for how much current flows through, we're going to use that equation. Once again, current is charge over time. So we're going to color in, just so I'm keeping my colors consistent, I use blue for charge and green for time. Current, I used red. So here are the equations and units again. I'll move myself up here. So we're just filling in the values. 4 coulombs for the charge, 5 seconds for the time. 4 over 5, you get 0.8 amperes. So that is our answer. So this is pretty straightforward. We can associate current with other measurements of circuits like voltage that we talked about yesterday. But we're not there yet. We're just going to keep with the standard, standalone equation for current for now as charge flow over time. And just as an FYI, this current we just solved for, 0.8 amps, that's plenty enough to kill a human. You only need about 1/10 of an amp, maybe 2/10 of an amp, to be lethal to a human being. So current is most definitely the dangerous part of a circuit. Hopefully you realized in that video, or rather those pair of videos about the Van de Graaff generator yesterday, that voltage is actually not dangerous at all. All those signs you see around electrical, big electrical boxes, and the fence says, say, danger, high voltage. High voltage is usually associated with a high current, but voltage itself is not dangerous. It's the current that will kill you. Anyway, I wanted to mention a few more things about the circuits we'll be studying as far as current goes. Once we get into actual circuits, which won't be until the week after spring break, I think, we're going to talk about the current flowing through a circuit in one direction. So you can see in the picture here, we have the current coming out of a battery. Let's say it's going clockwise around the circuit. It goes in this one direction back through the battery, over and over through any appliance hooked up in that circuit. That is called a direct current circuit, or a DC circuit. Most circuits in real life are actually alternating circuits, where the current flow goes one way for a while and then it very quickly flips back the other way and goes completely opposite. That's called an alternating current, abbreviated AC. In physics, we're only studying direct current circuits, but I'll tell you that no matter which way you assume your current is going, nothing changes. You can take a look at the graph on screen here. Direct current will have just a constant voltage to provide the constant current in a circuit. Meanwhile, an alternating current, like our outlets here in our homes, they are very quickly reversing the voltage, therefore reversing the flow of current very rapidly. Electrons are flying through at millions of miles per hour through the wires of our circuits, though. So the fact that it's very quickly reversing doesn't actually change anything about the circuit, as I mentioned before. You can also appreciate the graph of the alternating currents voltage. Should look pretty familiar from our waves topic. Huh? And one last thing, like I mentioned before, but here's just a picture of what I said. Even though we pretend current may go one way around a circuit, if you think of the other way, it's completely identical in all other measurements. Conventional current flow, the way we kind of pretend current goes as far as engineering schematics go, is that the positive charges flow around the circuit. But in reality, we know that electrons are the particles that move, not the positive protons, but the negative electrons. And so they will wrap around the circuit opposite the way our positive current would go, which actually doesn't exist. But again, it's all the same no matter what. So you pick a direction once we get into circuit study and stick with it, nothing will change. That's the end of our circuits discussion. You can take a look at exit ticket number 2 now and add any details to your term maps you can about current. I'll see you in the next video tomorrow. Take care.